Edbook worms, hi! Thanks for joining me in this lesson. We will be continuing with the last part on work. Now here we will be focusing on work done by forces that are acting on an object that's moving along an inclined surface. Now I realize that most learners are having trouble answering types of questions on objects on an inclined surface, and really it's not much of a problem. First of all, let's consider an object that's moving up an inclined surface, considering, or rather assuming that the incline is frictionless. Now if we were to consider the forces that are acting on that object, let's say it's the applied force as well as the force due to gravity, precise. Because if you were to leave the object on the incline without any external forces, then the object would slide down the incline because of the force of gravity. Now, because of our definition of work, the force applied must be in the same direction as the displacement of the object. Now, if you consider gravity, gravity is acting downwards. However, the motion of the object is along the inclined surface. So by now, you can already tell that, if you recall your grade 11 work, you can tell that it's actually the parallel component of gravity, the component of gravity that is parallel to the inclined surface that is responsible for the motion. And if you were to revise your grade 11 work, you would remember that the parallel component of gravity is equal to the force of gravity multiplied by the sine of the angle of the inclined surface. So that would be F parallel is equal to mg sine theta. So, just to get you into the rhythm of calculating work done by gravity on an object along an inclined surface, consider an object on top of an inclined surface. And let's assume that the inclined surface is frictionless. You leave this 10 kilogram box on the inclined surface and then it slides down. Now, it slides down over a distance of let's say 2 meters. Now calculate the work done by gravity. How do we go about this? Well, from our definition of work, we know that work is equal to the force applied on an object multiplied by the displacement of the object. Now as we analyze our problem, we know that the force that is being applied on the object, or rather force that's doing work on the object, is the force due to gravity. But particularly the component of gravity that is parallel to the inclined surface, which is mg sine theta. So by now you can already see that our force is actually the force of gravity that's parallel to the inclined surface, and we found that by mg sine theta, where we use our angle of inclination. Now as we finish off the rest of our formula, it will just be the usual delta x cos theta as well. Now you remember that cos of theta tells us whether or not the force applied is doing positive or negative work. Now in this case, whether gravity is doing positive or negative work depends on whether the object is moving up or down an inclined surface. Now if the object is moving up an inclined surface, it makes sense that gravity should be doing negative work because it's going in the opposite direction. However, if the object is moving down the inclined surface, then it's moving in the same direction as gravity. Hence, gravity does positive work in that case. Now, as we substitute all our values into our equation, we have our mass, which is 10 kilograms, our gravitational acceleration, which is 9,8 meters per second, sine of, let's assume that our angle of inclination is 30 degrees. Then right in our formula we would substitute 30 degrees. Now our delta x, we know it's 2 meters, and then since the object is moving down the slope, we would have ourselves substitute cos of 0 there. Now, as we narrate it down, we can see that our force that is parallel to the inclined surface, it sums up to 49 newtons. And then overall we have the work done by the parallel component of gravity as being 98 joules. Alright, now solving these problems of objects along an inclined surface shouldn't really give you much of a problem now that I have taken you through on how to calculate the work done by gravity. Now, this is the point where we transition from work to energy, okay? Now, how do we bridge work and energy? Well, we will start off with the work-energy theorem, which states that the work done on an object is equal to the change in kinetic energy of that object. Now, if you think about it for a little while, it makes sense that when you apply a force on an object and that object moves, the chemical potential energy in your body is changed into the kinetic energy of the object. Now, how is that facilitated? By means of the force that you are applying. Now, we will also continue to move throughout talking about the law of conservation of energy, which states that the total mechanical energy of a system remains constant. In short, energy can neither be created nor destroyed. It can only be transferred from one form to another. Now, going back to explaining the work-energy theorem in detail, if we were to outline this and put it in a sense of a formula, you would know that your total work would be equal to your change in kinetic energy. Basically, that would be work net is equal to final kinetic energy minus initial kinetic energy. And that's what it says. And with that formula throughout, you can play around with it to find out the mass of the object or the initial or final velocity of an object that's moving up or down an inclined surface or throughout a horizontal slope. Now, in the next lesson, we will do in-depth problems that have to do with the work-energy theorem. And I guarantee you it's going to be awesome. I'll see you in the next lesson. Cheers.